why Flint, Michigan, of all places? There was a story came out a couple of years ago about the bad water quality. And what I wanted to do is just play about a minute of a video off of YouTube to explain what the crisis was.
You drink that? People have dumped in this river forever. It's like we're in a cesspool.
My tub, you should see it, it's brown.
And then come the headlines. An American city failed to provide basic protections to its citizens, and now the children of Flint have much higher than normal levels of lead in their blood. Rick Snyder, governor of Michigan, has apologized.
I'm sorry, and I will fix it.
President Obama declared a national emergency.
You can't shortchange basic services that we provide to our people.
And now 2016 presidential candidates are starting to weigh in.
The governor of that state acted as though he didn't really care.
Lead poisoning is terrible and terrifying. No amount of exposure is safe. And there's evidence that years after we got it out of paint, gas, and more, it contributed to a drastic drop in crime in the 90s. The city has switched back to cleaner water, but the effects will last decades. We take clean water for granted. How could this be?
As they showed the one graph of crime going up and then going down, and then they showed the graph of lead going up and going down, that would be a classic case of you don't know if it's causation. It could be correlation, not causation. So a mean lead level of 15 parts per billion is considered safe, while anything above 15 parts per billion is considered dangerous. So Mr. Wilcox believes the Flint water is unsafe. So he takes a random sample of 200 households. He finds the average lead level of the sample is 16.5 parts per billion. So statistically, if you look at the entire year, just because it's more than 15 doesn't mean that the entire population of water, if you will, is more than 15. It could be that we just happen to randomly get a sample that was higher. So let's identify the parameters and statistics. So the population who they were testing potentially was all Flint households. The parameter, in this case, it's a mu, is the true mean lead level. The true mean or average lead level. The sample was those 200 households, as stated right up here in the problem. And the statistic was the number that was derived from the sample. In this case, it was given as X bar as 16.5 parts per billion. Now, we're in a new unit here. This new unit is called hypothesis testing. And there are two hypotheses. The first hypothesis is called the null hypothesis. And you can see it's represented as H sub 0. Now, sometimes 0 is called not. I think they call it that in England. Or sometimes they call it nil. If you've watched a little bit of soccer from the UK. But H sub 0 or H naught or the null hypothesis means that everything's okay. Everything's normal. Everything is as it should be. Nothing to worry about here. So that hypothesis is that the mu was 15. Now, what if the mean was actually less than 15? Well, don't worry about it. That just proves your case even more. And we always will, in the null hypothesis, we'll use an equal sign. Well, we don't need to use the greater than or less than there. What I would say to you is that if you got something less than 15 for your sample, you wouldn't even be doing this. You would have called it a day a long time ago and said, oh, must be clean. Now, the next one is H with a subscript of A, H sub A. Now that stands for the alternative hypothesis. In this one, we are going to use a greater than sign, and we're going to point toward the direction of the sample. We're still going to use the 15 number, but we're going to say greater than 15 because that's the direction the sample was in. The hypotheses always use the parameters. They don't use the sample. So you're going to be using mu or you're going to be using P if it's a proportion. Mr. Wilcox simulated taking 100 samples from safe water and assumed that the null is true. This is exactly what we did in our project when we were back in the classroom. When we got the Chromebooks out and we did Rotten Tomatoes, we did a simulation assuming one number is true, and then we were going to see how often we get the other number. So it says here, from the dot plot, estimate the p-value for an x-bar of 16.5. Just like our project. In fact, that's why I had us do the project. Well, here's 16.5 over here on the right, and there's only 3 dots that are 16.5 or greater, right? Because it would be worse to have more than 16.5. Well, there were 100 samples. So 3 out of 100, there is 3%, right? This is a 3% we're in danger number. But then there's that key word again, interpret. Interpret the p-value. So here's how you do that. You say, assuming the null hypothesis is true, and that means water is safe, there is a 0.03 probability of getting your mean of 16.5 or greater. We say or greater because it could be worse. So we're going to assume the null is true unless we have convincing evidence otherwise. Now, here's where the convincing evidence comes in. Is 3% statistically significant? Okay, so remember back to the project, we would say, is 3% rare? Based on a 5% cutoff level, 3% is rare. It would be rare to get 16.5 just by chance. So the logic then is, well, then your null hypothesis is probably wrong because it's so difficult. It's such a small probability to get it by chance. That means your assumption was wrong. So based on the p-value, what decision, or should Flint keep the water or switch to bottled water? Is the p low? Yes. Since, well, not p, well, the p-value is this 3%. P for probability, right there. Since p is less than 0.05, we reject the null. The water isn't safe. There were 2 possibilities. There were 2 options that we had. One was to reject the null. We don't say we accept the null. We don't say we accept the alternative hypothesis either. And I think the best example of that is in a court of law. So let's say someone has been arrested, they're going to have a trial, and the judge says, well, how do you plead? Now, you're supposed to be able to plead one of 2 ways. It's either guilty or not guilty. Now, sometimes a defendant will say innocent. In the court of law, you're not really trying to prove that anyone is innocent. What you're trying to do is you're trying to prove that they're not guilty. Now, there's a difference. Innocent means that you absolutely didn't do it. Not guilty means there isn't sufficient evidence that you did it. You see, those are 2 different things. It might be almost impossible to prove someone is innocent. Where it is possible and does happen that you can prove that someone is not guilty. In other words, they haven't made the case. The case isn't strong enough. So in this case, we don't say that we're going to accept the alternative. What we just say is we're going to reject the null in favor of the alternative, or we're going to fail to reject. Now, you can look it up. There's another meme on that. It's, I think it's Justin Timberlake or something like that. And he's saying, girl, I failed to reject you. Like, as a backhanded way of saying, I love you, right? You would never say to someone, hey, I failed to think that you're gross, as a way to say I love you. But in statistics, that's how we have to do it. Now, let's suppose the decision to reject the null is wrong. What would be a consequence of this error? So let's think it through, okay? So the water is unsafe, they're thinking. So what do? They buy bottled water. So Flint buys bottled water, wrong kind of buy. Flint buys bottled water, and spends money doing that, right? And spends money they didn't need to spend. Why? Because if the decision is wrong, that means the water was safe. Flint buys bottled water and spends money they didn't need to spend. Now, in real life, they did buy the residents bottled water for a while, but you saw a little bit in the news story. People couldn't they couldn't take a shower. The water was so dirty they didn't even want to take a shower with it. Now, it's pretty hard to take a shower with bottled water, but the city did temporarily buy them bottled water. Okay, now suppose that the p-value is really 0.14. So there's a 14% chance of randomly getting the result. Is that rare? No, that's not rare. 5% is considered rare, 5% or less. So should Flint keep the current water or switch to bottled water? In this case, since the p is not low, and since the probability is actually greater than 0.05, that means we're going to stick with what the null says. So we fail to reject the null. And consequence, or the real life context, is that means the water is safe. Okay, but let's suppose that decision is wrong. Let's suppose that the water isn't safe. Okay, so if that decision was wrong, that means people are drinking unsafe water. That's bad, right? So oftentimes, because the alternative is so bad, that even though the science says it's probably okay, sometimes the politicians will go ahead and spend the money anyway, because if they get this decision wrong, they're going to get voted right out of office. So number 8, is the error made in question number 5 or question number 7 more serious? Well, you would have to say that question number 7 is more serious. Right here. You don't want people drinking unsafe water. Now, these types of errors that were made in 5 and 7, they're not your typical kind of error. When we think of an error, we might think in baseball when a player, should have caught something and he drops the ball. Or, when you're in the kitchen and you drop a dish and you break it. No, I had an error, right? Well, these errors are not anyone's fault. They're not our fault. It's not that we did the math incorrectly. We did the math correctly. It's just the conclusion was in error. So on number 5, we call this a type 1, and they usually use Roman numerals, type 1 error. This is when you reject the null, but you shouldn't have. You should have kept it. Now, the second one, obviously, then is a type 2 error. Type 2 error means that you went ahead and kept the null, but you should have jumped over to the alternative. You should have rejected it and gone over to the alternative. One way to help you kind of get a handle on these two is the idea of a fire. So in number 5, if the decision is wrong, then that's like saying there's an alarm, but there was no fire, right? So imagine you're in the kitchen and you smell smoke and get your phone, you dial 911, the fire department comes, and somebody was just lighting a match. Really wasn't a fire. What's the consequence of that? Well, the fire truck had to come out. You kind of wasted some people's time, but overall, what ends well, right? But a type 2 error is usually more dangerous. In this case, this is fire with no alarm. So you're in the kitchen, start a grease fire. Oh, don't worry, it'll burn itself out. Catches the wall on fire. Nobody called the fire department. What's the consequence of that error? Well, maybe you've just lost your house. There are these two types of errors that we can make. And in the context of each problem, usually one is a lot more dangerous than the other. Now, this brings up another point. Since our decision making is based on this 5% rule, right? 5% is considered rare. That could lead us to an error of one type or another. So sometimes we'll change the standard of what is rare. So instead of P being 0.05 or 5%, maybe if it's a really serious consequence of a type error, we might say the p-value is 1% or even 0.1%. You know, like when people's lives are on the line, you might lower the p-value. But if it's sort of inconsequential, or, you know, it doesn't matter as much, won't result in loss of life, maybe just loss of money, then maybe you raise the p-value to 0.1, 10%. You could take our recent coronavirus as an example. Is the coronavirus as dangerous as we thought it was? Well, recent reports are suggesting no. But out of an abundance of caution, and you'll hear politicians use that phrase, an abundance of caution, it was better to be, and here's an old saying, it's better to be safe than sorry. And so that's what you've seen, a lot of safe than sorry. Why do we close school? Better to be safe than sorry. We didn't know if anyone would die, but to remove the possibility, then we went into quarantine. Well, that raises the question, well, then could we have committed an error the other direction? Yes, we could have. Sometimes it's hard to know what the alternative history is going to be. If the p-value, and the p-value just means the probability of some decision, right? If the p-value is less than, now, we've always said 5%, and I just raised the idea with you that sometimes we can change the 5%. It's called alpha, and that's a Greek letter. Alpha is our level of the test, or the level that we're going to jump to the alternative. Usually alpha is 5%. If the p-value is low, then we're going to reject the null. But if the p-value is above it, fail to reject. We don't say accept, we say fail to reject. Now, if you can do the first one, if the p-value is low and that leads you to rejecting the null, then you can say that we have convincing evidence. That's what convincing statistical evidence is. Okay, and then over here, we're going to talk about the two types of errors, number 2 and number 3. So we're going to break this into a table, 2x2 table. If the null was true, if the original statement we make is true, but we reject it, then this is called the type 1 error. The other diagonal, these are good decisions, because the first one in the upper right-hand corner says, oh, the alternative was true, and since you rejected the null, that means you're supporting the alternative, so you did the right thing. The other good decision was the null hypothesis, the one you started with, was true in actuality, and you failed to reject it. In other words, you stayed with that hypothesis. So that's good. That last box has got to be type 2 error.